got here for you is a great satellite image of the 1992 Hurricane Andrew. And this satellite image, which basically is showing us energy intensity across these cloud masses, gives us a great idea of the structure of this storm. And I'm going to talk about the storm surge along with this image. So here we've got the breadth or the extent of this storm, and you can kind of see from the state lines. You've got the Mississippi River here and Florida out through here, the Panhandle, Alabama, Mississippi, Louisiana, across here. This is a really large storm, and it was the first largest storm that really created a lot of damage in North America and really changed the insurance industry. Really broad storm here across this. This is where the low pressure cell is the greatest, across this segment here. Out here on either side, we've got high pressure cells. So high pressure cells all the way around, and a big low pressure cell that occurs here. Low pressure cell in the eye as well. So here in this diagram, I want to point out just a couple of things before I talk about storm surge and the damage that can be done. Is we've got a wall, which is this outer edge of the storm that gets polished by the rotation of the storm. That's out here, and you can kind of see it's friable. It's got a lot of texture to it, but when you look across here, it's polished. And it is polished, but there's lots and lots of residual cloud that the satellite image picks up. The eye wall of the eye is the velocity is much greater, the spin is greater, the polish is greater, and the difference between this fast rotating eye of the storm, or eye wall of the storm, and the center of the storm is enormous. So you go from very intense winds to virtually no winds in the center, and there's stories about birds being caught in the storm, and they just fly around in the eye of the storm until the storm is able to dissipate. All storms have this configuration where you've got a center calm portion of the storm. Some of the storms, like snowstorms, will have a weak eye, but nonetheless it will have an eye of some sort. So we'll get what appears to be two storm events. So as this particular storm hits landfall and you're living here, you're going to get this part of the storm, and then you're going to get a little reprieve where it's calm, and then you're going to get the backside of a storm. If you get hit by the edge of the storm, you don't get what appears to be two storm events. You get one storm event. But if the eye crosses right above you, you think the storm is over, but it's only halfway done. So this is what we've got happening here. The pressure difference, now I just made the note that snowstorms work the same way, and so do tornadoes. There's an eye to a tornado as well. We're just talking about scale difference and intensity difference with the three of these storms. But what we've got here across this landscape, or if we want stormscape, is a big low pressure cell. And water is fluid, so it's going to react to the pressure difference. And a proxy to that would be, make yourself a pan of Jello, and when it's set, rest your hand in one side of the pan of Jello, and what you'll see is the Jello is going to depress under the weight of your hand, and then it's going to bulge where your hand isn't. That's how the water is going to react as well. Where the pressure is high, the water depresses, and where the pressure is low, it's going to lift. If we then create a vacuum, which is a low pressure cell under this storm condition, that water is going to lift under that storm and depress out here where the pressure is higher. So when this storm is approaching land, what ends up happening is the water depresses a little bit, but then as the edge of this storm approaches land, then we get a huge rise in water called a storm surge, and a wall of water then hits the landscape. So if this is the edge of our storm here and there's water underneath it, we've got water that's depressed under here, and then we've got a bulge of water here. So a wall of water is about to hit this structure right here in a matter of minutes. So we've got here just about the start of this wall of water, and it's this wall of water that hit New Orleans with Hurricane Katrina that did all the damage that we're still recovering from today. So lots and lots of damage, mostly from this storm surge. The wind and the rain are secondary influences. As this storm penetrates inland, as does every hurricane that then is rotated inland from the Coriolis effect, it no longer has a source of water to generate more latent heat into the cloud mass above, so the cloud is going to dissipate in intensity. The wind velocity is going to diminish, and it's going to reduce in categories of a hurricane and eventually become a tropical depression again, and then a storm. Now in 2006, a hurricane hit just west of New Orleans and found its way up the Mississippi River. And the Mississippi is a gorgeously hot body of water because of how opaque it is, how much water is coming out, and so all the industrial activity along that river. So it tracked up the Mississippi, and as it tracked up the Mississippi, it did lose intensity because in Mississippi, even though it's a large body of water as a river, it is not the Gulf of Mexico or the Atlantic Ocean. So it lost some intensity, but it didn't lose as much as intensity as if that storm would have hit somewhere else. So this storm tracks all the way up the Mississippi. It's rotated clockwise, goes along the Ohio River a little bit, and by the time it gets to Ohio, it's a tropical depression. And if you do recall, or if you know folks that were around the time of this tropical depression, they'll tell you that trees were uprooted in Mahoning Valley. Mill Creek was just a mess. We had power lines down, and the cleanup took weeks and weeks and weeks. So a tropical depression is significant, and when the conditions are right, Ohio can see tropical depression size storm events consequently. Now, talking about storm tracks and storm generation, a couple of slides that I really do like are these that show the Coriolis effect rotation both in the northern hemisphere and in the southern hemisphere here, and where we see the genesis of most storm events. So out here in the Atlantic and in here, and this is a little perplexing, we get the zones where we have a tropical depression. Those winds are going to push across the Atlantic and push across the Pacific. And as time moves along and we move along these warm bodies of water, then we move from a depression to a storm, tropical storm, and then in here we start to see the amassing of hurricanes, and then we get a clustering of hurricanes. Now these are statistical averages, so right here is where we're going to get a lot of hurricane style winds being produced at 74 miles an hour or greater, and then through here we get more and more, and we get this cluster right here where we're supposed to be creating baby storms, but now we've got fully mature storms generating on this side of the Pacific Ocean, which is a little bit perplexing. So I want you to question, why is it that we're getting storms where we should be just having baby storms here and then over here on either side of the subcontinent of India, and then even here in the Indian Ocean? Why are we getting so many? So I want you to kind of question that, a little thought experiment for you that I'll help you with in a minute. So just to be clear, generating tropical depressions, tropical storms, and then through here we're getting our creation of typhoons here in the southern Pacific Ocean, in the southern Indian Ocean as well. But what's going on over here? Why are there no hurricanes in the southern Atlantic? I want you to consider size. I'd mentioned size a little bit earlier, right? When I talked about size and number of uh, tropical storms in the Pacific Ocean relative to the Atlantic. So what does this tell you about this space in here, which is not generating any hurricanes, right? Or consequently right here, why we're not generating any hurricanes. So that's a question for you. Now, as the Coriolis rotates, we're going to rotate these storms clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. So if we're generating or we're starting to generate storms here, most of these storms are going to rotate through here and rotate in the Atlantic here. It's these storms, once they become hurricane in size, have the potential to interact with the continent, all the way through to Central America, up through, we know, is going to hit New York State and perhaps even a little bit higher. So the same function of rotation is going to see the Gold Coast of Australia all the way across to Darwin, seeing the same sort of effect. And then we see Madagascar and this portion of Africa experiencing the same. With these rotations. So I said I was going to give you a little bit of a hint on why we have all of these mature storms happening on this side. When I was a grad student at Texas State, one of my advisors was Dr. Dixon, and Dr. Dixon was watching the storms because he's a meteorologist. And he was predicting that the storm that was coming through was going to hit Brownsville, Texas. And all of his students were like, no way, that's not going to happen. And we were watching this storm, and early on with storm prediction, a large area is usually defined. We'll often say 5-6 days out that we don't know where this storm's going to hit. Somewhere from, let's say, Cuba all the way to South Carolina. And everyone living across those landscapes are like, are you kidding? That's like, how am I supposed to react when you're telling me it could hit Cuba? So the reason for that is the ocean temperatures are quite variable. They warm, they're cool. Ocean currents are moving temperatures around, and you've experienced this when you've been in a swimming pool and you hit a warm patch of the pool or you hit a cold patch of the pool, right? This is the same phenomena, especially in the Gulf of Mexico here. And when the temperatures change, the velocity of the storm changes. It either ramps up and spins faster, or it spins a lot slower, and that's going to change the trajectory of these storms. So based on how these storms hit these different bodies of water, their speed's going to change, their direction's going to change. So as we move from 5 days out to 4 days out, the cone of contact becomes more and more narrow, until we're 1 or 2 days out, and we have a much better geographic idea of who's going to be influenced by these storms. So we're watching this storm come in, and it's going to hit anywhere from North Mexico, through to the east side of Houston, really large area, and it eventually hits south of Brownsville, Texas, which is right on the Mexico border, and skips right across Mexico, where we know now it's going to lose energy because there's no water source to keep it going, until it hits the Gulf of California, which is some of the warmest water on the planet. Be a great place where we've got, this is one of the ecosystems, nurseries of the planet, lots and lots of biodiversity in here because these waters are so warm. Hits this warm body of water and then re-amplifies, and the Coriolis effect brings it back across, and it hit Brownsville, Texas. So Rich Dixon was a happy person because he was right, but he was right for the wrong reasons. So this is just an appreciation of how these storms can be so unpredictable and how they can change direction. So why are all these big storms right here, right? If it came across this girth of land, and this girth of land is much more narrow, I want you to consider that same thing for over here. All right.